I'm really happy to be here to talk to you about hot rocks and their host stars. Can everyone hear me okay in the back, online? I don't know. Yeah, okay, great. So this talk is going to be about exoplanets and specifically focus on sort of rocky exoplanets orbiting nearby M-dwarf stars. So the great promise of studying exoplanets is that there are a lot of them. Right, we will never be able to study exoplanets to the same level of detail that we can the solar system planets like Earth, Mars, Venus, even the moons like Titan. But we have a strength in studying exoplanets of sheer numbers. And so maybe we can learn something on a statistical level about exoplanets, planets in general, and planetary systems. So to start that, let's actually talk about what this sample is. And I'm going to focus on the rocky part of it, but we'll zoom out first and just see the great wealth of exoplanet systems that have been detected. These are all of them as of last week. We have just hit over 6,000. Very exciting. So here they are arranged in planet mass, or rough M sin I, and Earth masses as a function of the orbital semi-major axis. So how far that planet is from its host star. There are a few things you might notice about this sort of population of planets we have. One is that there's a big lack of planets in the space that overlaps where we actually know about planets in the solar system. This is a detection bias. It is much easier to detect bigger things closer to their stars than smaller things farther from their stars. There are some actually, though, real features here. For example, this kind of wedge cut out. This is sometimes called the subjovian desert or the sub-Neptune desert, where basically it gets really hard to hold on to an atmosphere when you're this hot, unless you're massive enough, and then you can really hold that atmosphere tightly. So with this information, we kind of make these broad brush strokes categorizations of planets. So you have your hot Jupiters, kind of self-explanatory, Jupiter, but much closer in, so it's hot. Sort of warmer, cool Jupiters. You have some very young hot things that are detected via direct imaging. And then down here, you have the small planets. This is where we're going to spend most of our time today. And these are can be kind of categorized as these sub-Neptune / rocky planets. So what do we know about these planets from the sort of statistical perspective? So to do that, we have to look to actually how these were detected. So this is now the number of planets detected as a function of discovery year and colored by the discovery method. This is a really nice image that came out as a result of the 6,000 number being hit. So it's a little bit cleaner than the one I used to use. So that was great timing. So the Kepler telescope, this launched, I used to think this was like common knowledge, but now there are people who've started in the field after the era of Kepler. So here we go. So Kepler launched in 2009. It's one of its reaction wheels, or two of its reaction wheels, failed by 2014. But in this prime mission, this was a statistical mission. It pointed at the same patch of sky for 4 years, gathering data that whole time. And from that, we have generated quite an incredible sample. There was an after sort of mission of Kepler for a little while. It is finally fully retired. But note that of the 6,000 planets we've discovered, over half of those alone are detected by Kepler. So this is still the biggest statistical mission in exoplanets we have to date, and this will maybe change with the launch of the Nancy Grace Roman Space Telescope. So what did we learn from this? We detected all these planets. What did we learn? And Kepler actually taught us something many things that are very profound, but specifically in thinking about small planets, is that if you look at the number of planets on the y-axis as a function of size, so Kepler measured planet size relative to the host star. One, it's that small planets are the most common type of planet orbiting stars in our galaxy. And two is that these small planets, things less than about 4 Earth radii, can have these kind of two broad categories that we roughly refer to as the smaller rocky planets and the slightly larger sub-Neptunes, which we think are some sort of rocky core with some sort of volatile enhanced atmosphere. This is something we did not know before Kepler launched, and it's something very real that we have learned from the statistical power of exoplanets. What a nice win. But now we want to go a little bit further. So radius right? So these are the Kepler radii. We put radius now on the y-axis as a function of planet mass. We get a little more of a sparser population around these small planets. And why is that happening? When you're looking for a radius, Kepler was a big photometer, it was a big light bucket. So you could detect the radii of things out to many, many, many parsecs. Well, like 100 parsecs, that's a lot for me. But if you want to actually measure the mass of those things, you need a very high precision spectrograph. And once you're smearing out your light, your signal to noise goes down. And so it's much harder to get the mass of a small planet than for, say, a much larger planet that's giving you a lot more tug on the host star. So if you were to look at this, you'd think that gas giant planets were the most common. That is, again, a detection bias. So we've kind of kept the radius and the histogram there on your right to remind you that these are still the most common planets. It's just harder to detect their radii and their masses. But if you can, this gives you a very powerful property, which is this bulk density, and this kind of bulk, density and a bulk composition. So let's actually zoom in a little farther into this region now where you have the small planets. And if you break down these kind of curves of isocomposition, you'll see that we actually have planets, right? Each one of these is a well-measured planet in radius and mass space, and they cover parts of parameter space where we have planets like Earth and Venus that we know very well. You'll also see that in these purple curves, they've taken this kind of Earth, I've taken rather this kind of Earth composition and added just a little bit of very light material, for example, hydrogen. This adds basically no mass, but it really puffs up the radius. And so that's how you kind of get these volatile rich planets in the top right, and then these sort of rockier like ones down here. This can only take us so far though. So I pointed out Earth and Venus here. Earth and Venus have the same bulk composition, but we know that Earth and Venus are very different, right? We live here on Earth with our nice oxygen and our surface pressure that doesn't crush us. And over here on Venus, this is not a very hospitable planet. So to actually get at the difference between Earth and Venus, it's not coming from the radius and mass, it's really coming from actually measuring those atmospheres. And so that is the kind of next frontier of characterization that we can do for exoplanets beyond the properties of mass and radius, the kind of core properties. Okay, so if you want to sort of try to work on this frontier, you actually have to detect the atmospheres, which is easier said than done. One thing that we go after is this thing called the M-dwarf opportunity. You want to look for a small planet, you want to get that tiny signal that's changing as a result of the planet's atmosphere around some core. You want to look at a smaller star where your signal goes up. So just to illustrate this, a terrestrial planet, I'm sorry, I keep hitting the mic, terrestrial planet orbiting an M-dwarf, you have a lot of pros there. It's a small, low mass star. Your signals for transits and radial velocities go up. There's also a lot of them. They're very common in the solar neighborhood. If you wanted to look for a sort of truer rocky planet analog to sort of what we have in the solar system, you go around a sun-like star, that's very large and massive, very small signals, and there's just not as many nearby. But there's no free lunch, right? These M-dwarfs have shown to have much higher stellar rates of stellar activity, much longer into their lifetimes. These can make detections difficult. There's also cool star spots on the photospheres of these M-dwarfs that can actually produce water. There's water in those atmospheres, and so they produce signals of water that, and if you're trying to look for water on a planet, this is contaminating. So there is some hope and idea that we actually will move to look at more sort of more solar-like stars, because you can avoid some of those pitfalls. This is a nice illustration because everyone loves a good illustration of an active star. This is kind of the concern that people are thinking about when it comes to rocky planets around M-dwarfs and will they have atmospheres or not. All the advantages for detecting a rocky planet around an M-dwarf mean that that planet is super close to its star, far interior of the orbit of Mercury. And so any kind of coronal mass ejection, even just flares, there's a higher chance it will intercept that planet, and this could be dangerous for maintaining a planetary atmosphere. So we want to detect rocky planet atmospheres, but we've kind of ended up in this place where we're asking, do rocky planet atmospheres even survive around M-dwarf hosts? And as this has become the thinking, we kind of want a little bit more of a theoretical sort of concept to follow. And that's going to come in the form of this cosmic shoreline concept, which is a rough concept, right? So this is, I'll sort of say what I mean by that. This is the, on the y-axis, we have like the irradiation of the planet, what we think is sort of cumulatively over the planet's lifetime. So we're already making some assumptions about the age of these host stars as a function of the planet's escape velocity. So if you have a very high escape velocity, you know, it's much harder for atmospheric particles to be lost. If you have very low escape velocity, maybe your atmosphere flies off more easily. And if you, this line here is a sort of power law is the escape velocity to the fourth power. And this is completely drawn by eye based on the solar system. So this totally works for the solar system. If you have a bunch of, if you look at the solar system planets and the asteroids and the moons, this line holds. But the common denominator for the solar system is the sun and everything that sort of grew up around the sun. So it is a proposal that perhaps this cosmic shoreline exists in a more universal way, but we don't really know. And so what this is kind of morphed into is, does this shoreline or some version of it, maybe slightly moved around, maybe adding some curvature, does this apply to the rocky planets orbiting M-dwarfs that are the sample where we're looking for these atmospheres? Okay, so that's the kind of question. Now we go atmosphere hunting. There's a couple ways we do this. You can look for a transit. When the planet passes in front of the star, light filters in through the planet's atmosphere. On the way to our telescopes, we get some imprinting of molecules that might be in that planet's atmosphere. You can watch when the planet goes behind the star, get some thermal measurement in the infrared. Thanks to James Webb, we can do this now. Or you can sit and wait for a full phase curve, and obviously that gives you the most information. So transits, this is kind of the easiest one to do because you get the largest signal from the planet going in front of the host star. So let's take a look at that first. This is what a transit with JWST looks like. This is a rocky planet, GJ486b. The transit depth and the precision of this that you can see by eye and these broadband, these two broadband transits is exquisite. We have never, you know, just to look at figures like this pre-JWST, you would never show an unbinned version of it. You would certainly never show the smeared out version where you have time on the x-axis and wavelength on the y, and that blue band in the middle is the planet transit. So the stability and the precision is transformative. Great, so let's measure, let's take that wavelength and that and this transit light curve, and let's make our transmission spectrum, see what molecules are in this planet's atmosphere. So transit depth is a function of wavelength. Each of these data points is a measurement of that transit shape. And you can now compare this to some forward models. So for example, some kind of really, 1,000 times solar metallicity atmosphere. You can try looking for some methane. And you can see that, yeah, can you see this? Yeah. So, this kind of curve here, well, that doesn't really fit too well. And this sort of bump from carbon dioxide, not really either. But if you kind of squint, that blue line looks pretty tantalizing, right? It kind of fits those data points. I mean, a flat line does too, but let's try. Let's try looking at this one. And I showed this paper because this is like a great paper that illustrates this, right? So you get really excited about that, like reduced chi-squared of 1.01. But if you do a more careful job, and if you actually try to ask the question, is this water in the planet's atmosphere or water in the host star? What you get is basically, you can't tell the difference, right? So in the bottom, this blue family of retrievals does fit the data really well. That represents water in the planet's atmosphere. The data are fit equally well by water in the host star itself. This is not a one-off phenomenon. This has been happening many times since the launch of JWST, and it's also not something that we were surprised by. This has been known for a while and really nicely written up on this paper by Ben Rackham called the transit light source effect, where you basically have to take into account that the chord that the planet is transiting across the host star is not, that underlying chord is not representative of the whole star. These stars are not homogeneous. So if you're covering up a part of the star that doesn't have many of these cooler spots, those cooler spots then get a disproportionate influence on the transmission spectrum you're picking up. Remember, we can't resolve any of this. This is all, we're inferring this. And this effect gets worse towards the blue. This was not as much a problem before James Webb because we didn't actually have the precision to tell the difference. Now we have higher precision data, we have to worry about this effect, and that's what we're seeing.
Can't that also put molecular lines in? Because this limb darkening is also molecular, has molecular components.
Yes, yeah, it's tied up very much also with how you parameterize your limb darkening coefficients, and that can be dangerous. Yes, yeah. If you see anyone that's fixing their limb darkening coefficients, be suspicious. Okay. Okay, so like this is great, but maybe with our higher precision data, we can try some other techniques. As I said, the phase curve is going to give you the most information. The problem with the phase curve is that you're sitting and waiting for the planet to go around and around. It's expensive, it takes a lot of time. But here's what you can get out of it. One, you're looking for two things. You are looking for this maximum, oh, sorry, let me explain this better. We have flux as a function of orbital phase. This piece is when the planet is going behind its host star. This big chunk here, that's the transit. It's way too deep. We kind of cut that off so you can get the sense of scale here. So you're looking for this maximum flux. So how much light is coming from the star plus planet system. Then when the planet goes behind the star, you lose that light from the planet. And this difference is how much flux is actually coming from the planet. So you're actually detecting photons like from the planet itself, which is pretty cool. The other thing you're looking for is this offset in the peak brightness and the point of the occultation. Why this matters, and you can kind of see in this heat map here that is derived from this data set. If you have some atmosphere around this planet that can move energy from that substellar point around to the cooler day side of or night side of the star, you might actually see this peak offset not at the substellar point, but slightly shifted. I'm sorry, and that would show up in this position of the peak flux versus when the occultation happens. Okay, so the question is, these are sort of two points of information we can get from the phase curve, but can we get them without sitting on the planet's orbit for so long? And I think the answer is yes. You will never get as much information, but you can compare this offset versus the change in peak flux based on different kinds of atmospheres. Okay, so this is what I call a theory paper, because you should have like an occultation here, right? You'll never see the back of the planet or the front of the planet if it's behind the star, but it's fine. You have the planet to start, it's just like this, except they haven't made the dip. Okay, planet to star flux ratio is a function of orbital phase, so just like the previous planet, or previous figure, but in theory form. And as you can see, these are calculations done for 3 different real terrestrial rocky planets, and then the different colors are different surface pressures. So 0.01 bar, that's a little bit more than the surface pressure of Mars, up to 100 bar, that's a little more than the surface pressure of Venus. Earth is 1 bar. And as you can see, relative to this phase 0.5, when the planet is predicted to go behind the star, you can pick up these shifts for the higher surface pressures, those yellow lines, but it's not so much. The shift is pretty small. You actually get a pretty large change in the maximum flux though. So that's where the greater information content is, which means that if you can just measure this maximum flux, that gets you a pretty good amount of the information, even though it's not getting you the full phase curve. So the answer here is to go for this eclipse, sort of an occultation or eclipse. That's when the planet goes behind the star. Yeah. Okay. Many advantages to an eclipse that we've gone over now. It's efficient, more efficient than a phase curve. You need to worry less about these unocculted star spots because the planet is not occulting them. The stellar face is not changing from before, during, to after the planet's occultation. We can especially assume this because the rotation periods of these stars are usually on order 100 days. They're not changing much on the few hours it takes for the eclipse to happen. There's also this thing called the CO2 bonus, only I call it this, but I'm trying to get it to catch on. So this is basically the fact that, so in this configuration where you're watching the planet move behind the star, you're measuring this light from the star plus planet day side, and then the difference when the planet goes behind. This depth, especially towards these infrared wavelengths, can be measured, and you can make a prediction of what this depth should be if there is no atmosphere on the planet. You can make a prediction for what that depth would be if you just have some kind of atmosphere smearing that energy around. You get a really big advantage if you put carbon dioxide in that atmosphere. And that's because there is a really deep, really well measured absorption line of CO2 right at 15 microns, right here. This is the 15 micron CO2 bonus. I say it's well measured, and that's important because there are some issues with line lists looking at molecules at the kind of hotter temperatures that a lot of these planets are at. But Venus is extremely rich in CO2. We have measured this in Venus extremely precisely. We also have this feature in Earth. Earth has CO2, not as much, getting more, but we can measure it as well. So this is like a really solid feature we can look for. And that's important because it gives you this extra difference between the atmosphere case with CO2 and the bare rock case. So it's kind of a narrow question of atmosphere, but it is one that we think is at least robust. And CO2 is a common molecule. Why not look for it? All right. Okay. So here we go. Here's the cosmic shoreline. Does it apply to M-dwarf rocky planets? This has been explored quite a bit now in the literature. So there's a lot of papers you can read about this. I'm going to focus a little bit on this sample of planets. This is the Hot Rock Survey. This is the large JWST Cycle 2 program that I lead. And we have 4 papers out now on this. The goal here is to look at these 9 planets and try to make this search for this CO2 in the atmospheres. Let me say one thing about this. This and the planets in purple, these are not statistical surveys. These are geo programs, right? It's a large program, it's a general observer program. The idea is to go after the lowest hanging fruit, right? That's why they're all kind of clustered over here in this no atmosphere less likely part of the diagram. These are easier to look at, and it is more of a fishing expedition. No one is claiming that these are sort of a statistical assessment of this parameter space. Okay. Change, please. Okay, so just a brief overview of the survey. As you can see, I've zoomed in really tightly on this radius mass space. So these are planets with really well measured radii and pretty well measured masses. They span some range of stellar mass. So these are all early to mid M's, no late M's. TRAPPIST, everyone else looks at TRAPPIST, so we went for these other ones. They have different planet installations, different surface gravities. This is ultimately a very tight population. There's not a ton of this is a very small parameter space, what I'm trying to say. And crucially, I do want to point this out because it'll come back later. All of the stars have equilibrium temperatures between about 300 and 800 Kelvin. So these are not ultra hot. They're sort of in this Venus-like kind of regime, and a little bit hotter than Venus. So it's always good to look at your raw data. I'm an observer, so I hope you can see with the contrast here. This is the raw PSF of JWST at 15 microns with MIRI. These are two different subarrays. That's why one looks bigger than the other. It's not about the star on the sky. You can see there's this sort of central peak, your classic PSF, and then you actually get this hexagon, right? Because JWST's segmented mirror actually reflects that. So you can see that, and you get these also, we call these the central peak, the petals, and the snowflake. And the snowflake is these other kind of reflective pathways you get as the light goes through the optics of the telescope. Okay, I think we have time for a fun fact. So to sort of stress maybe how close these systems are, I know a lot of people here work on sort of galactic scale things. LHS 1478, b, the planet that's orbiting this star, this system is about, well, I'll do it this way. It's almost 60 light years away. It's not very much. It's around like 20 some parsecs. I'm saying it in light years because this is the first frame taken in this time series and in this program. And the light from this image left that system on June 6, 1964, which is within a human lifetime for sure. If you look up what happened on that date, that was actually the first time the Rolling Stones were broadcast on TV in the United States. So a great day for the US.
It was a great day at that star today.
I was gonna say that. You ruined my punchline. Well, it was, yes. So about 60 years later, those photons were intercepted by James Webb. And yes, now they're listening to, I don't know which album that would have been. I should have looked what their single was back then. Beggar's Banquet or something. Okay, great. That's a fun fact. These are really close by. Let's though draw our aperture. Let's like take a look at where most of the flux is, which even though you can see these sort of extra patterns, most of the flux is still concentrated in this central PSF. And if we zoom into that, or rather plot that central PSF, we're gonna do the one on the right there. This is what the light curves look like in the individual pixels of MIRI. This is impressive because you can see actually, I'll show you how you can actually see how stable this telescope is over the course of several hours. So you have here these kind of counts that I've averaged per pixel. That's why the extent looks the same in all of them. But the number of counts is also shown by the color bar. So the darker the color, the more counts, so you have the most in the center. If James Webb wasn't stable and it was drifting, you would see a kind of, you'd be able to see that in this image. You'd be able to see a kind of drift of the sort of darker pixels relative to the lighter ones. You don't see any of that. These are extremely stable pointings. We do take multiple observations. So this particular planet, HG 260655b, we took 2. This was the first one. This is very nice. The second one looks like this. And if I go back and forth a little bit, you can definitely see a change that's not just a sort of change in photon noise type scatter. There's a lot more systematics, there's a lot more astrophysical noise happening in this second observation. And so the analysis of these data, naively, when we first got that, I was like, oh, great, we'll have like 9 papers out in a year. No, it's much harder than that. And luckily, I don't have to do this myself. I have a really nice team. This is my co-PI, João Mendonça, who I think visited here a couple of years ago. He was very excited that I was coming. He really liked it. He does a lot of things with GPUs. He'd love to be invited back. Okay. So yeah, so these are all the great people who work on this project. I'm going to highlight a couple of results. I don't have time to highlight all of them.
In that
actually.
previous plot, the gray bar was the transit.
Yes.
That's the transit. So
It's an eclipse.
Eclipse.
No,
right.
not with your, not unbinned. No, the eclipse signal is very small. Yeah, I'll show some more. Yeah, this is maybe easier to see because it actually has the binning. So this is actually that first data set, the Rolling Stones one. This was a bit, this was a strange data set for 2 reasons. One is that the idea was to take 2 observations of this planet and stack them together. This was the first observation. looks pretty good. You get a detection of the eclipse that's not statistically significant. That's why we took 2. The second one has this very intense systematic. We don't know why this is happening. We've considered the option that it's a flare from the star. It doesn't seem to fit other flares we've since seen at 15 microns. We cannot figure out what it was in the sort of pixel level of the data. Anyone else is welcome to try. This is publicly available data. But the point is, we got this really frustrating, tantalizing result where you can't, Plune, August, who did this analysis, you can do injection recovery tests, and there's just no way to pull out this level of signal from this data. And that sucks because this one not statistically significant detection is tantalizingly low. Again, not statistically significant. This is not a claim of an atmosphere. But you would have hoped that if we had a second observation and you could do your, divide by √2, then this would have been a really interesting result. Plune did a really nice work and published this. She also then went and got a bunch more JWST time to follow this up with MIRI LRS and more MIRI imaging. This is a cycle 4 program. We have not actually gotten any data yet. I think the first one's scheduled for December. But stay tuned. This could be really exciting or not. We'll see. Okay. Another paper from the project I want to highlight. This is one by Mark Fortune. And this is to sort of highlight what what we're sort of developing as a from the data analysis side, right? Mark actually went to the pixel level to try to detrend, to try to analyze this data. So while I just drew a circle around and like summed up all the flux, Mark had this idea to sort of reduce the data on a pixel level light curve basis. And he came up with this GP that considered 3 things. One is flux conserving systematics. These are important because you can have electrons that move from one pixel to a neighboring pixel. And when you're trying to measure the exact flux in this pixel versus this pixel, that messes you up. So this is known as called intrapixel capacitance. Interpixel capacitance. And the idea is that all those electrons are there, they're just not exactly where they're supposed to be. And so this is the flux conserving versions. You can see like this goes down where this goes up, and all of this has to sum to 1. You can then have another kind of systematic, which is independent pixel systematics. This can happen, perhaps you get a cosmic ray hit on that pixel. You now have some extra flux there. It's not what you're looking for from your star. It's not affecting the pixels over here, but you might want to downweight that pixel in your extraction. And then you have common systematics. These could be astrophysical. If you have some flare from the star, this should affect all the pixels the same way, right? Because the star is a point source to these pixels. So he actually took this method and he applied it. And in one of the data sets Mark looked at, there was indeed a flare that was caught. And in this GP predictive thing that he made, his GP found that, and downweighted those pixels. So the method works. It's a really great paper. He validates it in a lot of ways. To not at the end of the day get like a wildly different result. This is the black versus the red is the kind of classic aperture extraction, but we are learning a lot about the detector in this method. And so these are the kind of things that are sort of going to push us forward. So this is the sort of scientific result from that paper. Here you have flux. These are 3 eclipses stacked together. Mark gets this really nice result where this is likely a bare rock, or at least we can say this is not a planet that has more than 10 bars of CO2 in its atmosphere. That's what we can definitively say. Perhaps more than that is maybe it's also a bare rock, but that's less definitive. I'm running a little low on time, so I'm not going to go, or I'm not running low, but I'm just like a little behind. I'm not going to go fully into this because I don't know if people are so interested in like optimal extraction versus aperture photometry. Raise your hand if you're really excited about it. Okay, fine. Okay, great. Okay.
We all knew it was going to be you too.
I know Megan did too.
Okay. I can see it. We gotta move though. All right. So these are 2 observations. So observation 14 and 15. These are just sort of the names in the program. And these are two analyses. So observation 1415 done with optical extraction, observation 1415 done with aperture photometry. I'm going to get technical because it's now like just for YouTube people. So the idea, right, you'd think the optimal extraction would do better. It's supposed to downweight pixels with less flux, and therefore you increase your signal because you're upweighting pixels with more flux, higher signal to noise. This apparently, though, breaks down if you have more systematics in your high flux central pixels, which is what we think is going on here. This is why at the beginning, this ramp gets kind of blown up in the optimal extraction case, because those are the pixels that have to settle more quickly from why the settling happens. That's a bigger debate, but it does happen. We've seen a lot of data sets. And so even though both observations agree, once you get sort of down to this sort of settled level, but this was actually, we were surprised by this. We thought it would have been maybe the other way around. All right, we move. Okay, so we have, now here's the scientific result. Again, ruling out a sort of 10 bar CO2-like atmosphere and above. Natalie also tested some rocky surface compositions that the data agree nicely with. That doesn't mean that's what is on the planet, but sort of to illustrate the point that the atmospheric case is, that parameter space has decreased as a result of this. Not disappeared, just decreased. Okay, great. So those were our fishing expeditions. And you may ask, that didn't seem statistical at all. That's true. And so this is now where I've sort of sneakily had this on the figure the whole time. This is not my science work. This is my functional work at Space Telescope. I am contractually obligated to spend 0.2 of my FTEs on this, and I don't complain because this is a really fun project. It's called the Rocky Worlds DDT. We have a really great website. Please check it out. This is discretionary time from the director of Space Telescope, who has awarded 500 hours of JWST time and 250 HST orbits to go after this question in a more, not completely, but in a more statistical way. And you can see that by these yellow points that are on the figure. They're not just clustered around the easiest ones to detect, which are in that top right. They actually kind of perpendicularly cut along this cosmic shoreline line. The HST time is to characterize the host stars in the UV. I'll talk about that a little bit more. This is a really cool paper to check out, and I'm not just saying that because Jacob E. is a postdoc working with me, but in thinking about sort of how we can leverage statistics for these exoplanet samples, Jacob used this genetic algorithm to solve what's called the knapsack problem. The knapsack problem is you have a finite amount of sort of space and you need to fit as many kinds of things in that space as possible. What he also developed was this framework to say we want to optimize what you're putting in that space for 3 different cases of the cosmic shoreline. So the probability that the cosmic shoreline equals 1, that's like a hard line. That is a real true thing, and there is a hard cut, and everything on one side has an atmosphere, and everything on the other side has another. If you do that, you get a pretty good result pretty quickly. But if you have some blurring of that line, and even more blurring of that line, it gets tougher and tougher to actually find where that line is and if it's real. And so based on this, Jadud's recommendation is to go for, you might think like, well, why don't we just look at only the planets on this side? And it turns out that doesn't give you the same statistical weight as doing a wider and more shallow sample. So this is from his paper. We didn't pick these exact planets because these are sort of more like representative of the concept. We did follow that suggestion. So we went for a wide and shallow survey. So that means that there are 9 planets in this survey. It doesn't sound like a lot, but these ones down here are going to cost over 100 hours themselves. And 500 hours sounds like a lot. You can't actually get as far as you'd hope. But this is great. We have 2 data sets observed, and a lot more will be coming next year. Go to the website. We have updates all the time. Okay. I want to touch on the M dwarfs. because these have been lurking in the background, as it were, or in the foreground if it's an eclipse this whole time. Thank you. And we want to sort of like, what is the, we want to learn a bit about them, right? Because that's actually most of the photons we're getting are from the M dwarf. Oh, thank you, government computer. Okay, so it's easier to detect planets around what we call inactive M dwarfs. When I say an inactive M dwarf, as someone coming from the exoplanet world, that's like, okay, in this raw data, it's pretty flat. Compare the scales on the y-axis. So this is GJ486. This this system came up a little bit earlier, if you recall. And then this is AU-MIC, a known young variable planet. And as you can see, if you have a ton of modulation in your photometry, it's just going to be harder to find that little planet dip. These little B's down here, right? We actually have found a planet around AU-MIC, but it's much harder. Whereas here you can by eye see these little transit dips. Okay, great. Inactive M dwarfs. The thing is, even inactive M dwarfs, they're not just scaled down G stars. So you have some, this says flux in the habitable zone. It just means that these have been like normalized to some equilibrium temperature distance as a function of wavelength. The sun is in black, and GJ699, which I think is Barnard star, is in red. And what you can see here is that the UV flux, the flux in this ultraviolet part of the spectrum of the M dwarf, is larger compared to the bolometric flux of the star for the M star than it is for the G star, right? And so and it's actually even by this scale a little more overall. But the important thing is also the proportion. Why does this matter? Why does it matter that the UV and the extreme UV part is stronger in M dwarfs? Here's a rocky planet atmosphere. This is a sort of cartoon cross-section of some rocky planet that has an atmosphere. You have your surface, you have your stuff happening down here with interior-exterior exchange. But as you get to the higher levels where you have photochemistry, so this is light coming from the ultraviolet that breaks apart molecules, where you then get constituent parts and maybe they're reformed. This happens on Earth. Oxygen gets broken apart and then you get ozone, and then it goes back to oxygen, and that's a nice cycle that happens. At the top of the atmosphere, XUV, so extreme UV and X-ray flux that goes that penetrates up there actually can blow off, can remove, sort of excite these atoms and molecules, and you can lose material, right? This is just sort of like genes escape. The thing that I want to impress upon you is that whether we're using transmission spectroscopy or we're looking at emission, or if there is any atmosphere there, no matter how we look at it remotely, we are most sensitive to the top layers of that atmosphere. So it matters a lot more what's happening in the photochemistry than what's going on down here. We might not be able to tell what's going on down here. So if we detect anything in these atmospheres, it's going to be mostly driven by photochemistry, by reactions driven by the host star. Okay, so now we care about what's happening in the ultraviolet of M dwarfs. It turns out we are not good at modeling M dwarf spectra at high energy. So this is some flux as a function of wavelength. This is a real star, LTT 1445A. The lines in sort of orange and red, those are real data. So this is from HST STIS and Gaia. I have not done any special processing to this data. You just plot it out, they match because these are both excellent telescopes that measure flux correctly. The stellar models, which are very good, and let me really stress, because I know people work really hard on these stellar models. There's a lot of physics that goes in there. Honestly, I don't know. They're hard to make. They don't match. They match really well. They match really, really well as you go sort of towards the optical, right? It's like 700 nanometers out to here. They can't figure out how this extra absorption is happening. This is an active area of research. I think we will figure this out. Maybe it's clouds. We don't know. But the point is we're off by many times, maybe even up to an order of magnitude. And so this is kind of messing with our ability to take these models and understand what kind of chemistry we should be looking for. So right now, the gold standard is to just measure it. And also, maybe if you measure enough, you can do that, machine learning magic and like back out, you know what I mean? Okay. So there's another problem with M dwarfs, right? Which is that I've sold you on this like inactive M dwarfs, still important to measure, but then you go and measure them and you realize they do not behave the way you thought they would. So this is GJ486, our favorite inactive M dwarf that I measured with HST and the ultraviolet. And this is one visit of HSTs. These are 3 orbits, right? There's little breaks because of the Earth occultations. And I've been, without his permission, using this quote from Jacob Bean that I dug up from an email for several years now. So it hasn't come back to me yet. He wrote in an email that this might be the quietest M dwarf observed to date with extreme precision radial velocity. And yet there are 2 flares, big ones in this data set. You can see them by eye. And not only can you see them, you can fit flare models to them. And you can back out how much energy at these wavelengths is in these flares. That's great. Let's compare it to the population of M dwarf flares that we have. So this is a cumulative flare frequency as a function of equivalent duration. This is sort of a measurement of the flare energy, and this FUV, far UV 130 just implies it's with the same HST filter. So we're comparing apples to apples here. The one slightly cheeky thing I've done is that this study for the flare frequency to make this histogram used many M dwarfs, and they had like many HST orbits per star. I just like have 3, and I'm kind of backing out these values. So this is not like a statistical comparison, but it is accurate in that if you just took those orbits from GJ486 and knew nothing else, you'd think this was an extremely active star, right? These are 2 really high energy flares happening within 3 hours of each other. Is GJ486 some like anomalous extreme flare? I think the answer is no. I think what is really happening here is that these M dwarfs have cycles of activity just like the sun does. And what we don't know is the rates of those cycles and how intense those cycles are. And so we're kind of stuck getting these little snapshots and extrapolating them to all of this M dwarf's behavior and its influence on its host star. So what's the solution here? And this was a much more fun thing to plug before this mission call got canceled and will maybe happen next year. But I'm going to keep promoting it anyway, because one day maybe we'll have this. Is a proposal for a small explorer mission called ESCAPE. And the idea here is to get extreme UV and far UV spectroscopy of more than 300 stars, ranging from F stars down to M stars. There's also going to be a deep monitoring component to this survey that's going to take 24 targets, including some M dwarfs of interest, and really spend a lot of time staring at them. The idea is to look for flares and coronal mass ejections. So this is the statistics we need for the M dwarf side. Unfortunately, we might not get it very soon, but this is a doable concept. Okay. So. Right, okay, so I'm almost done. All right, so what have we learned here? Right, we have a sample here, but we don't quite have the statistical strength behind it to make the sort of statements that we can about rocky planet atmospheres that we can about the occurrence rates. That's something we're still working on. This is a really active area of research. And I think that in a couple of years from now, we'll have a much better idea of what's actually going on here. But there was a really interesting paper that came out earlier this week that was really intriguing. And maybe there is a trick that if the planets are hot enough, you can start to say something about their atmospheres. This is a paper that was accepted by Joanna Teskey et al. And this is brightness temperatures. This is kind of like how these are measured mostly at infrared wavelengths, but it's you're basically saying like how hot is the day side of this planet. This is the measured day side effectively as a function of the irradiation temperature. And the important thing is you can think of this dashed gray line as like the maximum temperature bare rock line. And you can see these are all the planets that I've been talking about. There's actually even 2 that came out more recently that aren't on here, but they're all basically following this gray line until you get up here. And now you have this sample of planets, and let's be critical here. This is a very big error bar. This is a very big error bar. 55 Cancri does not orbit an M dwarf. It's a really weird planet around a G star. And TOI 561 has some discrepancy in the data reduction that's leading to these data points. However, it's tantalizing. It's intriguing. If this holds, what this is saying that if your planet is hot enough, I mean, these are extremely high irradiation temperatures, right? These are almost as hot as stars. You will have some sort of molten magmatic surface that can potentially be outgassing volatile material that is leading to the presence of an atmosphere. So this is like very interesting, and I'm certainly going to keep watching to see what happens here. So, but this is very exciting. Maybe this is something statistical we've learned. Okay, I will conclude there. So basically, we are leveraging the sample of planets we have to try to figure out if rocky exoplanets around M dwarfs have atmospheres. Understanding these M dwarfs is really key to understanding the planets. And this is kind of groundwork for future missions, for example, Habitable Worlds Observatory. I'll stop there. Thank you.
Questions for Hannah?
So you showed this very nice piece of experimental design work that you did, which you were talking about knapsack problem.
Oh.
I would call that experimental design.
Sure.
You're trying to answer a question. I wanted to ask you a super high level question about it because we think about these kinds of problems a lot here. And you know, in cosmological problems, it's important to have volume and it's important to be able to measure the things you're measuring. But whenever you write down a well-defined problem in cosmology, you always get pushed towards doing a ton of things really like at 3 sigma. Like when you do the information theory or whatever, it always says do tons of volume at 3 sigma, not less volume at 5 sigma, because the volume is so important. And then you get your data and there's some systematic problem with your spectrograph and you actually can't do your science with it, you know? And right now you're in a situation where you really are learning for the first time about systematics in these instruments. So are you confident that this sort of, because I was just very triggered by you saying that it pushed you towards wide and shallow. Are you concerned about that, or do you feel like the systematics are, and I guess I'm just more asking generally, like how mature is this whole system? You know, like how mature is this work?
Yeah. I can see why that's triggering. Yeah, it's a good question. I think I'll answer it from my like space telescope half of my brain. So the understanding of the instruments is good, but I would confidently say there is more way to go. But the data will be the same. So getting better data reduction techniques, that data is always there. So the legacy value is strong. Additionally, the wide shallow survey did have what we were looking for in that it could at least say something about this question. Whether or not it's definitive, right, a 5 sigma, 7 sigma result, the idea is that this is like a ground level, groundwork laying kind of survey. All of the data will be taken in secondary eclipse at 15 microns with mirroring. No one could ever claim, right, that these are just 2 different reductions. These are the same data point. No one would ever claim that this one data point, wherever it is detecting an atmosphere. right? Even here, right? This tantalizing one, it's not statistically, you go after more, you go more, you get follow-up. So the idea was to, in one fell swoop, get a big groundwork sample that the rest of the community can then build off of in their own creative ways. Ground-based data, more JWST time, however you want to do that. So it's, yeah. So we're not trying to overpromise. We're trying to start
Good.
a movement.
I'm very happy with that answer, and I think it's obviously going to have high legacy value. But one of the things that we struggle with is it's hard to get those concepts into an optimization. You know, you're talking about optimizing a program, and a lot of the important things don't really appear in the objective function that you're optimizing.
Yeah, and I will say that we are sample limited. I mean, we right. This was, you know, this is an exercise that Jacob did. The reason we didn't just take this as our sample is because, oh, well, you look closer, the mass measurement on this isn't very good, or this one, the star's too far away, or this one has some other problem. And you end up in this, you know, it looks like maybe we could have chosen from like 4 or 5 planets here, but really there were like 2 that fit enough other criteria. We had enough other information that it would even make sense to throw 100 hours of time at it. So we had to balance that as well. And that's kind of reality of the universe.
I'll ask that.
Okay.
So this is really cool stuff. So you've made a compelling case that JWST is doing a really good job, and that with the like new level of precision that we get, we need to think more about how we're modeling like instrument systematics, how we're thinking about the stellar contribution. Are there also things in the planetary atmosphere models that we need to think about more?
Yeah, you're getting into dangerous territory. So, yes, I can kind of say like, here's like two ideas, and there's many, right? People have grumbled a lot about planet atmosphere variability, right? Do you always have the same atmosphere that you're probing all the time? If you have some, you know, huge volcano, you know, this can change the emergent flux you'd be measuring. So this idea that we rely on, you can just stack all these observations together and drive down your error bar at square root of n. We don't know. We don't know. And you know, as we get higher and higher precision, future generation telescopes, that could be a question we address. We don't have that ability, at least right now. The other one is that you can actually think a lot about, okay, if these planets don't have atmospheres, or if they're very tenuous and thin, you're actually detecting flux from the surface of the planet. So what does that look like? Is it basaltic? Is it granitoid? Would you expect something very shiny and reflective? There's a good bit of literature that sort of says like, well, you could have this really highly reflective surface and that would kind of look like an atmosphere. Sure, like that, we have to sort of understand where our assumptions are taking us. But, you know, a planet that has a ton of space weathering, like, you know, Mercury is not super shiny and reflective. And that's because it gets blasted with you know, particles from the sun, and you get this darkening effect. So we kind of have to use, we're sort of like, you know, I say we take the lever, you know, we take the number of exoplanets and learn from that, and we can take that back to the solar system. We also sometimes take what we have in the solar system and sort of, you know, throw that onto some interpretation of these exoplanets as well. Now, I think that's actually a strength. I think like actually bringing those two fields together, there's a lot to learn from both of them. But it is assumptions. You know, we're always working with our list of assumptions in the back of our minds. So, yeah, I'm sure there's many more you could think of as well. But you know,
Just keeps us all in the job.
Okay. Sorry, Megan.
Yeah, really interesting talk. This is kind of a super high level question. I'm going to ask it because it's right there on the screen.
Sure.
The thing about the cosmic shoreline grid that I've seen it pop up a lot in recent years, and I'd be curious to hear your take on of course, it's an approximation, right? But how much, like, how set in stone is this line here, right? Like yeah.
For the solar system, very well. I wish I'd had this figure because from the paper this comes from, which is like Zanley and Catling, it works really well for basically any body in the solar system. But they are all in this, right? They're all in the solar system. There's a common denominator there. So we don't need to know the sun's history to compare the atmospheric state of, you know, an asteroid versus Jupiter, right?
Okay.
So this, I mean, yeah, you could, you know, each one of these is a system. Maybe each one has its own shoreline. Maybe there's, you know, and they're probably, maybe if it is a little more universal, there's certainly some smearing, you know, some things will have, you know, outlier metallicities, something happened in this planet, in this system's planet thing. I mean, yeah, and you'd hope if you build up enough of this sample, you could actually draw this for the M dwarfs. And that's what we're kind of trying to do, but I would argue we're going to need a lot more in this sample to do
But
that.
how accurately, I mean, that depends a lot on this vertical axis, right? How accurately do you think we know things on that vertical axis?
Also not. Again, for the sun, yes, because that's, doesn't even matter what the history was, you can just look now. This, right, cumulative XUV irradiation. We don't even know how old, right? A lot of M dwarfs that we study are 5 gigayears plus or minus 4 gigayears. We don't know how old they are. But there has been work, and I don't actually, there's a lot of work in the M dwarf community. There's a paper by Sebastian Pineda that looks at this, trying to actually understand where the M dwarf saturation state is in XUV versus where that turnoff is. It's the same concept as what happens for FGK stars. You have this young, early, high energy saturation state, and then as you get some kind of spin down, some decrease in activity. But where that break happens for M dwarfs is different than the sort of FGK population.
Would move if you made different assumptions.
Yes, there's a great paper by Emily Pass et al. That actually does this for kind of correcting the later M's for some of that, and some of these points do kind of move around as a result of that. That's a really excellent paper. Adrian. Oh, sorry. Do you want to call on people?
No, you can.
Okay.
It's on the same point, so I guess it makes sense. First of all, really nice talk. But so I guess put another way, if you had, I know you're already talking about how this is a small sample and yada yada, but if you had ages for them, and you didn't have to just assume an integral of the cumulative flux, then would it be much clearer what's going on?
That would certainly be a game changer, yes. Much clearer, like to the degree that, okay, so now we know the age, but does that really tell us the history? Like, yeah, there's still some uncertainty there, but that would be huge. We do a lot of like measuring sort of bulk UV properties and rotation, and that does have correlations with age, but again, they're not tight. So a sort of mid-age M star versus an older one. I mean, yeah, that would be huge. If you have that ability. Yeah.
Yeah, I have a very general question. I think you touched on some planets in your sample. You said something that they could be comparable to Venus, and now it makes me very curious if what you've learned about those exovenuses and how those compare to our Venus, and if you could say something about the formation of planets like Venus from that.
This is a great question. How to answer? I don't know what slide would be good here. Actually, maybe this one. Right. That's it. Okay. This is a great question because I think the one thing we can say is that for most of these planets that we've investigated, you can rule out. This is going to be a long qualification here. You can rule out a carbon dioxide rich, so at least a percent by volume mixing ratio of carbon dioxide in atmospheres that have at least 10 bars of surface pressure. Venus has 96 bars of CO2 in its atmosphere, 96 bars, and it's like, something like 92% CO2, something like that. So none of these planets don't have this big CO2 bonus. So we are ruling that out. Like, that is something we've learned. That's really cool. I think it's really cool. It's a pretty narrow slice of parameter space to cut down, right? You could have water in these atmospheres, you get very different kind of things. The fact that we haven't detected those could mean that these planets don't have atmospheres. It could mean that they have these very strange, different looking atmospheres. And we probably think the difference there is the host star and how close these planets are to their host stars. Yeah.